Hi, welcome to my Physics 212 final video where I try to summarize a 4-month course in 8 minutes or less. So this should be good. I've decided I would like to go look at each of Maxwell's equations and discuss the concepts tied to each one, how we use it, and what that tells us about electricity and magnetism in this class and going forward in our other studies. The first of Maxwell's equations that we're going to look at is Gauss's law for electricity. So Gauss's law states that the flux through a closed surface is the charge enclosed divided by this constant that is the electric permittivity of free space. So let's unpack those different concepts there. So first, what is flux? Flux is this concept where we talk about something going through something else. So in this case, we're talking about the flux, which is the the electric field lines going through a closed surface. We can imagine that sort of if we had some charge and we put it in a box, and that box had all the field lines coming out from this electric charge through the box. The flux, the total flux through this box, which is a closed surface, is the sum of all those field lines coming through. So we should also discuss what is an electric field. Now, before we talk about an electric field, we'd usually talk about Coulomb's law. So Coulomb's law tells us that the electric force between two charges is this equation here. As we go and look at that, we see that it's very similar to gravity, and that it falls off 1 over r squared. There's some constant, and then in this case we use charge instead of mass and multiply them together. So our definition of an electric field is the force per unit charge. So what we do is we divide out the charge that we're affecting, and we end up with the electric field. It has a direction to it. In this case, we just define this vector r between the two charges that we're talking about. And then we can take the electric field at any point in space, this distance r away from the point charge we're talking about, and multiply it by the charge that we have and find out what the force is. This concept is the most useful for solving most of our problems. We're trying to find all the different forces. So it's very important that we be able to find these electric fields when our charge might not be a simple point charge. That's where we come back to Gauss's law. If we think about that for a minute and our concept of flux that we just discussed, and it being the field lines that are going through a closed surface, we can very clearly see that even if the field lines become more dispersed as we get farther away from our charge that we have enclosed, it's still the same amount of flux that goes through it, because even though it's more dispersed, you still have a bigger surface area. You're catching the more dispersed flux in. So really, Gauss's law seems to flow very naturally just from that sort of geometric look at what flux is. We're like, oh, well, it's what the electric field is over some area, and it just turns out to be related to all of the charge that's inside of that closed surface that has that area. So how do we actually use Gauss's law? Unfortunately, this surface integral that's in here is really a pain in the butt to solve. We can intuitively understand what it is. We have a dot product in here between the electric field and the area that we're talking about. We try to get around all of that, particularly in this class, to simplify it down so we don't have to actually solve that integral. In order to do that, we choose this surface that we're performing this integral over as something that is everywhere perpendicular to the electric field. So we call those surfaces Gaussian surfaces. And a really common example, if we have a point charge, we just choose, I know it's a poorly drawn circle here, but we choose a sphere so that the electric field lines that are all coming out by sheer symmetry, so that's what we're talking about with the symmetries, are going to be perpendicular to that sphere everywhere. So this dot product here, if we go and expand it out, is this right here. So we just have the two parts of the dot product multiplied together, and then we have this cosine. But if we've chosen that to be perpendicular everywhere, this cosine here goes to 1, and then we just have a times b. So that sort of collapses down this integral, so we end up with this here, and well, this will just integrate to the area. dA integrates to A, and the electric field is the same everywhere because of the symmetry. So we're done. And we have this sort of simplified down form that we can use anytime we're able to come up with these symmetries. So the rest of the problem that we're trying to solve when we use this is just finding what this enclosed charge is and what this area is. So usually we're trying to find that, for example, if it's a point charge, the radius away. So this area will end up being the area of a sphere. And if we're doing this inside some ball with a charge density, then the enclosed charge would be the charge density times the volume of that ball. If it's not a uniform density, we have to integrate. So there are more nuances into how we use this, but that's the crux of the whole thing, is getting these symmetries so we can get it down where we can solve it here without having to consider this really difficult integral. I've spent so much time on this particular concept because we use this throughout the rest of Maxwell's equations in different ways. We have to find these symmetries to solve these problems easily. So next we go from electric fields to magnetic fields. Magnetic fields cause this force to be seen on a charged particle or charged object that is moving. So a static object doesn't experience any force from a magnetic field, but a moving one does. Now, you might think, oh, well, a magnet, why that's not moving. Why does that experience something from a magnetic field, or why does a piece of metal move when you put a magnet near it? And the fact is, it still has moving charge. Magnetic materials have unpaired moving electrons that are charges and able to be affected by the magnetic fields. So the big difference we see in magnetic fields is it's proportional to the charge, but it's a cross product instead of a dot product. So I'm not going to get into the right-hand rule on this, but it always has a force that's perpendicular to the direction of motion. So it won't change the speed that something is moving when there's a uniform magnetic field, but it will change the direction that it's moving. This causes particles to move around in a sort of spiral pattern inside of B fields, which is really neat. And it's the other part of the Lorentz force, where the Lorentz force is just sort of this combination of the force that's felt on a charge by an electric field and a magnetic field. So we just take our charge we have, multiply it by the electric field, and its velocity times the B, or crossed with the B field. So the next of Maxwell's equations that we look at is Gauss's law for B fields, or magnetic fields, and it states that the net flux through a closed surface is zero. This sort of makes it the boring one among Maxwell's equations because we can't really solve anything with it directly, but it does state an important phenomenon about magnetic fields. So if we look at a magnetic dipole inside of this closed surface, and we go and look at the magnetic field lines that come off of that dipole, we find that even when a magnetic field line exits through one side, it's going to re-enter on the other side, and the net flux will end up being zero. So because there are no magnetic monopoles, these dipoles, they might have flux going through the surface, but the net flux will always be zero. So the next Maxwell's equation we look at is Amperes Law. Now this is the power tool for solving for magnetic fields. We use it similarly to how we used Gauss's law for electricity, but we note that this is a closed curve, not a closed surface, so that would be, say, a loop as opposed to a sphere. And we still have this dot product in here, and we just have to go and choose an Amperian curve. So we chose a Gaussian surface before to collapse this integral in much the same way. If we just consider a wire coming out of the page here, with some current I flowing through it, we know that the magnetic field is going to curl or circulate around that wire from the white hand rule. So we can just choose, in this case, a circle, so that's not a sphere, a circle of some radius away from that wire, and we'll know that this is parallel everywhere to the magnetic field. So we can exploit this fact in a few different ways. If we choose this loop here so that it is either parallel or perpendicular, then it's either 0 and we can ignore it, or it's 1 and we can simplify it. So this integral can be simplified down to, we know, same as before, the B field is constant, and dl is just going to integrate into L. Of course, we would also exclude any of that length that we had chosen to be perpendicular to the magnetic field. This lets us solve a huge number of problems where we need to find the magnetic field caused by a moving charge. This current is just the charge that's moving through an area per time. We call it I because that's convenient. But whether that's a beam of electrons from an electron gun or it's the current flowing through a wire, it's the same thing. Oops, I lied. That's not all of Amperes' law. There's this extra bit here that Maxwell found that is actually extremely profound, and that is that a changing electric field also creates a magnetic field. We'll see in the very next thing with Faraday's law that the reverse is also true. The very last piece of Maxwell's equations here is Faraday's law. In combination with the second term of Ampere's law, we see that electric fields, when they change, they create magnetic fields. And here, when we change the flux from a magnetic field through some loop, we also get an electric field. So a changing magnetic field creates an electric field, and a changing electric field creates a magnetic field. And they sort of can feed off of each other and actually just propagate through space on their own. This was the just incredible, immense discovery that led us to the entirety of electromagnetic waves, which gives us light, it gives us radio, it gives us so much more into our view of the universe. I'm out of time here, but that's Maxwell's equations and some of how we use them, and then the profound insight at the end that Maxwell found. I really enjoyed this semester with everybody. This has been incredible. I've absolutely loved learning about all these equations with everybody, and I hope everybody's not too upset that I went a little bit over on my time here. Thank you all so much.